So today's topic is on trajectory generation, and I'll motivate this in just a bit. So trajectory generation. Okay, so what's a trajectory? Well, in the past we have seen that in case of inverse kinematics, we wanted the end effector to trace, say, the circle or the asteroid, right? So that's basically a trajectory. And so we've done that in the past in the context of um, inverse kinematics, but these trajectories were static trajectories. So we had static trajectory. What I mean by static trajectory is that the trajectory was defined in spatial coordinates. So there is a x and y, and we specified the xy position, but there was no hint of time in the trajectory. Now, time is important, however, in case of a manipulator in the real world, because you can't get manipulators to move infinitely. They simply very, very fast to make motions. So in this case, when we're looking at trajectory generation, we will focus on dynamic trajectories. So here we will look at dynamic trajectory, where there is x of t, y of t, and z of t. Okay, so that's basically what we are going to do. Okay, so let me um, draw this graph of the joint q of t, or rather q versus time. So this could be a joint angle or a displacement if it's a prismatic actuator. And say we want to go from start position, let's call that q0 to end position, let's call it qf, and on the x-axis is the time. So the question is, how can you connect q0 to qf as a function of time? One option, well, you could do something like this, or it could be something like this, or let's say it could be just a straight line, right? So there are multiple options. And then here, maybe I want to go from T0 to TF for the time. Okay, so in robotics, the way people decide these trajectories is on either the trajectories are decided based on avoiding collisions with other objects, which is a reasonable thing to do. Sometimes, for example, in quadcopters, when there are no obstacles, you're interested in going from point A to point B such that you are reducing energy. Same thing for mobile robots and so on. So it could be based on some optimization criterion, or it could just be based on avoiding collisions. So we are not going to focus so much on generating these trajectories based on either of those two, but we will actually consider a different aspect, which is ensuring that the joint motion is such that it doesn't lead to unnecessarily uh, torquing the or jerking the manipulator, is what we're going to consider when we are looking at trajectory generation. Okay, so let me write this down. There are ways in which ways to decide which trajectory is preferred. So here are some candidates. One is optimization, minimize energy, minimize time. And we saw an example where we minimize the time for the car or even for the pendulum, which we did for homework. Another is obstacle avoidance, which is self-explanatory. And the third one, which is the focus of uh, what I'm going to do, is avoid unnecessary jerks on the manipulator motors. Okay, so that's what we are going to focus on, and so let me underline that. Okay, so let me get into more details what I mean by jerking or unnecessarily uh, loading the manipulator motors. Okay, so before we do that, let's take the simplest example of connecting Q0 to QF through a straight line. Okay, and let's try to figure out how can we figure out the expression for Q as a function of time. So this is really motivating you to the come to the, well, what analysis I'll do right now will actually motivate uh, jerks or unnecessary acceleration on the motors, and that will help us refine the choices we make. So by let's start connecting Q0 and QF by a straight line. Okay, and see what the consequences of that are. So let's, here the same figure, Q0, sorry, Q, T, T0, TF, point Q0, point QF, joined by a straight line. Okay, so what we are after is find Q as a function of time, right? Because once we have Q as a function of time, we can then send it to the robot joints, and the robot joint can execute that motion. So what we see is we want to ensure that at time t equals t0, Q equals Q0, and then at time t equals tf, we should have Q equals QF. Okay, so we notice here that there are two conditions. Okay, and so then we ask, what is the minimal order of polynomial we need to represent uh, this kind of relation between Q and time. Okay, and as you can see, it's from the graph, from Q of t plot, it's a straight line. So what we can do is we can define Q equals a0 plus a1t, which is the equation of a straight line, and then try to estimate what this Q0 and QF are based on these two conditions. So notice there are two conditions and there are two unknowns. So we can set up two equations to solve for those two unknowns. So here's how we proceed. So first, Q equals Q0. We sub in the value of t in the expression for the line. So we have a0 plus a1 t0, and then we have QF equals a0 plus a1 tf. Okay, so once we substitute that, we can now solve. Okay, before we solving, let me write this as a matrix, because that thing is going to be very powerful when we automate this using MATLAB. So here I'm going to write the left hand side is obvious. The right hand side, I will write it in such a way that the constants which are unknown are expressed as a vector. And all I need to now do is fill this matrix, which is going to be 2 by 2, because there are two constants. So that will be 1, because 1 multiplies with a0 to get me the first term. And the second one would be t0, because t0 multiplies with a1 to give me the second term. Similarly, I would have 1 and tf for the second row. Okay, so these are my unknowns. Q0 and QF I've given you. T0, TF is also given. So then I have to solve for A0 and A1, which I can do. So if you want, you can write this as B, this as A, and that as X, or AX equals B. And to solve this, we just say X equals in MATLAB a backslash b. So this solves for x, right? So solving that in MATLAB, or if you want, in this case, it's actually easy to solve it by hand. You get a0 equals, so solving, we have a0, a1 comes out to be 1 divided by tf minus t0, then q0 tf minus qf t0, and then the second line is minus q0 plus qf. Okay, so we've got a0 and a1. In other words, we've found out what q of t looks like. It's basically a0 plus a1t, where a0 and a1 are now computed by inverting the A matrix. Okay, so let me write that down. So q of t, after subbing in the values, is q0 tf minus qf t0 divided by tf minus t0 plus qf minus q0 divided by tf minus t0, whole things times t. Okay, so this is q of t. Now the next question is, what is q dot of t, which is the rate of change of position, right? Q dot of t, so the first term, which is a0, is simply a constant. So the derivative of a constant term is 0, plus the second term, when we differentiate with respect to time, we get qf minus q0 divided by tf minus t0. So note again that qf, q0, tf, t0 are both given to us, and so this term here is just a constant. So graphically, what we have here is q versus t is a straight line, q dot versus t is constant. Okay, so what's happening on the manipulator is that even though the position is changing linearly, okay, this is zero velocity, the velocity is zero, and then it just jumps up to whatever value you get from this expression, and then remains constant, and then it dies down to zero. So this is going to jerk the motors. So this is a transient. So this transient response can damage the motor, right? This is to say, if you're trying to, in a car, if you're traveling in a car, and if you try to suddenly go from zero speed to 60 miles per hour, then clearly that's going to cause unnecessary jerk in the car, and that's what you want to avoid. And that's exactly what is happening if we take a straight line. Okay, which means that how can we avoid this? Well, one way of avoiding this, so how to avoid this? Okay, so one way of avoiding this is we, in addition to specifying that the positions at the end points are specified, we also specify the condition that the velocity at the end points are essentially zero. Okay, so to fix this, what we do is we say q equals, so q of, I just write it as t0 is equal to qf. Q of tf is, sorry, my bad, this should be q0. Q of tf should be qf, right? This we already have. In addition, we also want to ensure that q dot at t0 equals 0, starts with 0 speed, and then q dot of tf is also equal to 0. So this is specifying the velocity at the start and end should be 0. So we look here and we see that we have 4 conditions. So clearly, if you have 4 conditions, then a straight line won't do it. You need to have more free parameters so as to get an expression which will satisfy all these conditions. So what we do is, in this case, we choose a third order polynomial, okay, because a third order polynomial has four constants. So what does that polynomial look like? Well, it's q of t equals a0 plus a1t plus a2t square plus a3t cube. And you can see that as four constants: a0, a1, a2, and a3. Okay. Next, we basically sub in these values of q and q of t. So let's write q dot first. Q dot of t is a1 plus 2a2t plus 3a3t square. And next I will sub in these four conditions and get four equations. Let me do that on the next page. Let me copy this. Okay, so this is for reference. Let me now sub in these equations. So first we have q0 equals a0 plus a1 t0 plus a2 t0 square plus a3 t0 cube. That's equation 1. Equation 2 is subbing in tf for t. That's equation 2. Okay. Third equation is q dot of t at time t equals t0, which we know is 0. So that's equals. So I'm putting t equals t0 in that expression. So I have a1 plus 2a2 t0 plus 3a3 t0 square. So that's equation 3. And then finally I put t equals tf to get 0 equals a1 plus 2a2 tf plus 3a3 tf square. This is 4. Okay, so we have 4 equations, 4 unknowns, and so we can solve for those 4 unknowns. Okay, now this is where it gets harder, right? If you try to solve this by hand, that is going to take a while. And so this is where I recommend using MATLAB. But before we can put that in MATLAB, we need to sort of shape these equations so that they are written as matrices, which can then be put in MATLAB. So I'm going to do that just next. So on the left hand side, it's pretty simple. It's just 4 terms: q0, qf, 0, and 0. So that's easy. So then there is going to be a matrix which will multiply with the constants, and the constants are a0, a1, a2, and a3. Okay. So the way we do this is the first line will give you the first equation, which I wrote down here. Okay. And I will need to write the coefficients of a0, a1, a2, and a3 over here. Okay. So let's start. So first is coefficient of a0, which is 1. Next is coefficient of a1, which is t0. Then we have coefficient of a2, which is t0 square, and then t0 cube. Similar thing happens for the second equation. So it's 1 tf square, tf cube. Okay, now we have the third equation where you can see there is no a0. Okay, if there's no a0, that means the coefficient which multiplies with a0 is going to be 0. Then we have the coefficient of a1, which is 1, 2 t0, and 3 t0 square. And then the same thing happens for the fourth equation: 2 tf, 3 tf square. So this is again b equals a times x, and you can solve for x, which is simply a backslash p or a inverse p. This is preferred by MATLAB because it makes the computations uh, tolerant to numeric rounding when the determinant is close to zero. Okay, so once we solve for a's in MATLAB, you get, okay, I'm going to write this. I have no space for this. I'm going to write this, the values of x on the next page. X equals 1 divided by t0 minus tf cube, and then there are four lines: qf t0 square, t0 minus 3tf plus q0 tf square, 3t0 minus tf, 6t0 tf qf minus q0, 3 times t0 plus tf q0 minus qf, and then the final equation is 2qf minus q0. Okay, again, I did not get this by doing these computations by hand. They were all generated by MATLAB. Okay, and I use a symbolic toolbox to do that. Okay, so once you get these values, then you can start plotting q as a function of time. So remember, we want to go from q0 to qf in time t0 to tf, and then if you look at the trajectory, you'll see that it's something like this, like an S shape. If you now look at the velocity, it's actually going to be okay, q dot as a function of time. It's actually going to start at 0, end at 0. So it will look like this. There will be a point where it reaches its peak, and here in this case it reaches its peak midway. So we've got, and why does that happen? Well, you can see here from the plot of q versus t that the slope here is 0, right? The slope on a qt plot is basically the velocity, and that's why you see that it is the velocity is 0. So slope is 0, which corresponds to this. Okay, so that's the velocity. What about the acceleration? If you look at the acceleration, you'll see that the acceleration actually is something like this. Sorry, this should be, maybe I should just put the t0 and tf to make it clear. t0 tf, t0 tf, and then t0 tf. Okay, the acceleration would be just like this. Okay, so what's going on with the acceleration is it's 0 at t equals 0, then it suddenly accelerates to some non-zero values, and just depends on how fast you're going, that acceleration will be more or less. And then again, once it reaches the end point, it's going to decelerate and come back to 0. Okay, so this is again a transient response. Okay, and if you have this transient response like this, you're suddenly accelerating or suddenly braking, then that is going to hurt your motors. So this can damage motors. Okay, so clearly this is not desirable. So then what you do is, to avoid this, what we do is we specify q at t equals t0 equals, let me just write it as q of t0 equals q0, q at tf equals qf. Okay, we wrote that down. We also specify that q dot at t0 is 0, q dot at tf is 0. And to avoid the acceleration from jerking at the start and end, what we do is we specify q double dot at t0 is 0 and q double dot at tf is 0. So we have 6 conditions. So we'll have to write a fifth order polynomial, something like this. And then solve for a's, right? So this is what we've done with the first two parts, and we do it for acceleration. If you want the acceleration to be 0 at t0 and tf, and clearly when you do that, you will see that. So once this is done, you will see that q dot, q double dot are continuous, right? What is, well, so this is, you can see that this curve is continuous, this curve is continuous, this curve is discontinuous at t equals t0, right? So we will basically get continuity for the position, velocity, and acceleration. However, q triple dot is going to be discontinuous. Okay, and then, well, if you want q triple dot to be continuous, then you'll have to specify another 2 variables, which would make the equations go from 6 to 8. You'll have a 7th order polynomial, and you'll do the math. Anybody knows what q triple dot is? What is it called? Q double dot is acceleration. What is q triple dot? Jerk, yes. So q triple dot is called jerk. Okay, so if you do that, you again will see that it's basically discontinuous in the fourth derivative. Anybody knows what fourth derivative is? What is it called?
Snap.
Snap, yeah. It's also called jounce. What about the fifth? Anybody knows the fifth derivative?
Crackle.
Crackle. And then the sixth.
Pop.
Okay, I mean, I'm sure many people have not heard of this. Snap, crackle, pop are the fourth, fifth, and sixth derivative. Okay, so the next thing we'll do is we will actually solve some, well, 2 problems. Here's the first one where I'll show you how to do this numerically instead of doing it symbolically. Okay, so the problem is as follows. Okay, find a time-based parameterization for a revolute joint of a manipulator. So we're only looking at a single joint. Okay, in principle, if there are 6 joints, you need to do this for all 6 joints. The joint should move from 0 to 0.5 radians from 0 to 1 second. So in 1 second, it moves 0.5. And then from 0.5 to 1, from t equals 1 to t equals 3 seconds. So if you want, I can maybe write it down so it's easier to parse. Q equals 0 to 0.5 from time t equals 0 to 1, followed by movement from 0.5 to 1 in 1 to 3 seconds. Also, the velocity of the joint at the start of the motion and end of the motion is 0. So velocity, or q dot, is 0 and 0 here. Should be 0. The velocity of the joint at the intermediate point at t equals 1, so that's the intermediate point, should be 0.2. So it's 0.2. Okay, so position goes from 0 to zero point 0.5 to 1 in time 0, 1, 3, and then q dot is 0, 0.2, and 0. So then the question is, uh, assume two minimal order polynomials of time, one for each movement. When we say minimal order polynomials, it means that just find the right order. So if you have, for example, the past problem when we took that straight line motion, we assumed it to be a straight line or first order polynomial. A second order polynomial is not the minimal one, but a first order is. So it just satisfies all the conditions. So when we say minimal order, it means that what's the minimum order you need. So what we need to do here is from 0 to 1, we need to have one curve. Okay. And from 1 to 3, we want to have another curve. Okay. I just randomly drew it. It's probably not going to be discontinuous the way I drew, but I just showed it that way. So it's kind of illustrative. Okay. So we need to find two curves, 1 and 2. Now, for each of these curves, we'll ask ourselves how many conditions are required. And then based on that, we will figure out what is the minimal order required. So for 1, which is the curve from 0 to 1, we have q0 equals 0, q1 equals 0.5. So we are given these two things. We are also given that q dot at 0 is 0, and then q dot at 1 is 0.2. So we have four conditions, which means that we need a, so four conditions, we need a third order polynomial. Okay. Similarly, for 2, we have q of 1, which is here, is 0.5. Q of 3, at time 3, we have 1 radians. Q dot at 1 is 0.2, and Q dot at 3 is 0. Okay, so we have four conditions. So we have third order polynomial. Okay, now one thing I want to mention is here I've explicitly said it's a polynomial, but it doesn't have to be a polynomial. It can be, you could put sines, you could put cosines. Instead of saying t square, you could say sine t, cosine, sine t, sine square t, and so on. Okay, uh, just that polynomials are much easier to write, and they actually encompass a whole range of values. That's why we use polynomials. Okay, so we have written down four conditions, 8 conditions, and we said there are 3 polynomials. What I'll do is I'll call this actually q1, just so that it's easier to uh, link them up. And then we said q1 of t should be a third order polynomial. Now, instead of writing it a0 and a1, I will write it with two subscripts. First subscript will mean that it's for the first part of the motion, and then I'll put the 0 to represent the constant term. And similarly, we have a11t. First one represents the first part of the curve. The second one represents the coefficient corresponding to t1, and then a12 t square, a13 t cube, and then we have q2 of t equals a20, 2 for the second path, a21t plus a22t square plus a23t cube. Okay, so we see that in total we have 8 constants which we need to find. So what we'll get is we'll get 8 equations, and those 8 equations will help us find those 8 constants. So I also need to get the velocity, so I'm going to do that next. Let me just do it on the next page. So copy this. Okay, so let me take the derivative. So q1 dot of t is going to be a10, sorry, the derivative of constant is 0, so that won't be there. A11 plus 2a12t plus 3a13t square. Then we have q2 of t, q2 dot of t equals a21 plus 2a22t plus 3a23t square. Okay, so that's the 4 equations, but now I need to get the 8 conditions. So I'm going to just go through this and write them down. Let me just maybe just copy the these conditions here, so it can make me much easier to show it to you. So copy this. Okay. Okay, now we're all set. Let's. So the next step is to write these 8 conditions in terms of the constant. So I'll be subbing in q1, q1 dot, and so on in these equations to get 8 equations. Okay, let's see how that goes. So let's start with this is part 1. Okay, so let's put q1 0 equals 0. So let's just put t equals 0 in this expression. So we have q1 0 equals a10, and then you can see the second, third, and fourth term is simply all of them are 0. So we have a10 is 0. Next, let's put since we had positions, let's just use the other position condition. q1 1 equals 0.5. So we have q1 1 equals a10 plus a11 plus a12 plus a13 equals 0.5. Okay, we're done with positions. Let's move on to velocities. I have the velocity formula down here. So let's put that. q1 dot at t equals 0 equals. So since time is 0, we have a11 plus everything else is 0. So equals 0. Finally, we have q1 dot at time t equals 1. So I need to put time t equals 1 in this expression. So I would get a11 plus 2a12 plus 3a13 equals 0. No, it's 0.2. Okay, so those are my 4 equations from 1. Let me just write them as 1, 2, 3, and then 4. Okay. Okay, now let's do the same thing for the second set of conditions. Okay, so now I have q2 of 1. What I need to do is I need to put time t equals 1 in this expression. So I'll do that. q21 equals a20 plus a21 plus a22 plus a23 equals should be 0.5. Next we have q23, which is this condition. So everything here should be equal to 1. So let's put t equals 3 in this expression. So a20 plus three a21 plus 9 A22 plus 27 A23 equals 1. Okay, that looks fine. Now let's move on to Q2 dot at 1, which is the seventh condition. So I put t equals 1 and I get a21 plus 2a22 plus 3a23 equals 0.2. And then the final one is Q2 dot 3 equals, last one is a21 plus 2a22, sorry, 3 times 2 is 6 plus 2 square, so 3 square is 9, 9 times 3 is 27, a23 equals 0. Okay, so those are equations 5, 6, 7, 8. Okay, that's a whole lot of equations, and as I said, this is really hard to solve uh, manually. You could do some things like you can see that A10 is 0, A11 is 0, so that's nice. You could potentially reduce it to 6 equations, but I still think that you will benefit from having an automated method of solving these equations. So what we'll do is we'll actually take these equations and make them into a matrix. That matrix will go into MATLAB and will give us the values for all these constants. That's what I would recommend. So let me do this slowly. Let me copy this to the next page and show you how to get the equation. It's just a little bit of bookkeeping. It's nothing too hard about it. Okay, we all set. Let's try to write these equations in one giant matrix. Okay, so what I'm going to try to do is write them as, let's see. So I would need 8 lines because there are 8 equations. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then I would have, since there are 8 constants, I would have 8 columns. Okay, so those are my 8 columns. And then these are going to be multiplied with the constants a10, a11, a12, a13, a20, a21, a22, a23. And then on the right hand side, I would have whatever is in the right hand side, which is 0, 0 0.5, 0, which is the third uh, third equation, 0.2, fourth equation, 0.51, 0.2, and 0. Okay, so I'm only left to fill this big 8 by 8 matrix, and that's actually simple once you put it in this way. So let's see, a10 is the first equation, so the coefficient of a10 is 1, so I need to put that here because this gets multiplied with a10 to give me equal to 0, so the other elements are all 0. Okay, next is this equation, so a10 is 1, a11, which is the next element, is 1, a12, third element is 1, fourth element is a13, so that's 1, and then we'll have all zeros. Okay, moving on, third equation, we have a11 is 0, which means the coefficient of a11, so note that a11 is the second element, so I need to put 1 here, not in the first place, so that's all 0. Okay, next we have fourth equation. So coefficient of a11 is 1. So since the first constant is a10, I need to put 0 here. Then I would have 1 for the a11. Then I'll have a 2 for a12, and then I'll have a 3 for a13. Then we'll have all zeros. So these are the first four equations: 1, 2, 3, and 4. Okay, let's do that for the second half. Second set of equations are 5 through 8. So again, if you notice, 5 through 8 have only constants for a to 0 and so on. So that's these elements. So the first four columns will obviously be 0. They do not really contribute anything to the second set of equations. So that makes it easy. So once you put zeros, now let's see how to write uh, equation number 5. So we have 1 which gets multiplied with a to 0. Then we have 1 which gets multiplied with a to 1. And then there is 1 for a to 2, and there's 1 for a to 3. Next, equation 6, we have 1, 3, 9, 27. Okay. Then we have, now note that we don't have a to 0, we only have a to 1. So I need to put a 0 for a to 0, first element. And then we have 1 for a to 1. And then we have, something is not right here. 1, 2, 1, 2, yeah, that's fine. So a to 1 is 1, and then 2, and then 3. Okay, that takes care of equation 7. And then 8, we have 0 for a to 0, because there's no a to 0 in the eighth equation. And then we have 1 for a to 1, 6 for a to 2, and then 27 for a to 3. Okay, so that's 5, 6, 7, 8. So you can think of this big giant matrix, 8 by 8 matrix, as an A matrix. Okay, I can call it whatever I want. And then we have X for the unknowns equals B. So 8 by 1, 8 by 1, and 8 by 8. Okay, so all I need to do in MATLAB is to do X equals A inverse B, or the better way to do it is to use the backslash. It will give you the same answer. So these will give you the coefficients of a's, or the coefficients of the two polynomials. Once you have those polynomials, the constants, you can then reconstruct the q1 and q2. And once you reconstruct q1 and q2, you can then do plots. Let me write the values I got for a1, 0, and so on. So a10 is 0, a11 is 0, a12 equals 1.3, a13 equals minus 0.8, a20 is 0.55, a21 is minus 0.375, a22 is 0.4, and a23 is minus 0.075. Okay, so what's the purpose of doing this? Well, we can, as I said, do some plots for q1, right? Q1 of t is a formula for involving a's, and q2t is also a formula. We can actually sub that in, use linspace to get the data points, and then do plots for q as a function of time. Sorry, this should be time, this should be q. So what you notice is that if you do this plots, you'll see something like this: 1, 3. So first half, okay, let me draw all the three plots: q dot versus t. So again we have 1, then somewhere here we have 3, and then finally we would have q double dot versus t. So again there will be 1 second and then 3 seconds. Okay, so the plots will look like this. For For position for the first half, it will look like this. Okay. For the velocity, starts with 0 and then it will go down to 0.2 because we made it uh, have a velocity of zero point 0.2 at time t equals 1 second. And then if you look at the acceleration, you'll see that that starts actually at non-zero value and goes down. Okay, so this is causes jerks in the motor, as we've talked before. Okay, and not recommended to have such jerks. So if, as I said, if you want to avoid this, you want to specify q double dot equals 0 at start and end, and then take the next higher derivative when you see that, which is basically snap, will is going to, sorry, jerk, which is the third derivative, will actually have these transients which are not good. So that's the first part. The second part of the trajectory, which looks like this. So it's continuous in q, so it'll go like something like this. It should end at 0, so I need to be careful here. I need to start like this, and then this is sort of close to 0 but not 0, 0.2. Okay, and here we start at 0.2 and we end at 0, so something like this. And then the acceleration is again discontinuous. It's actually slightly lower than the previous one. Okay, so those are the plots. What I will do is I'll give you a MATLAB file. See MATLAB file, and I'll post it on Blackboard, which actually starts off with the A matrix and the B matrix, which I derived earlier. It solves for X and then does these plots so that you don't have to really do them by hand or use a calculator. You can actually use MATLAB to do it. So as I said, in summary, once you identify the polynomials, it's just a matter of crunching in the numbers and solving the problem. Here is another problem, which I will sort of quickly lay down to give you an idea of how these things are done. Okay, next problem. Okay, find a time-based parameterization for a revolute joint of a manipulator. The joint should move from 0 to 0.5 from t equals 0 to 1 second, followed by movement from 0.5 to 1 from t equals to 1 to 3 seconds. So there's nothing has changed between the previous question. The layout so far is the same. Also, the velocity of the joint, the start and end, is the same. It is 0. However, the thing which has changed from example 1 is this part. The acceleration of the joint at the intermediate point at t equals 1 should be continuous. If you remember correctly, the last example, I said that the velocity at the point t equals 1 should be 0.2. Here, however, it's stated that the acceleration should be continuous at t equals 1. Okay, so again, what you'll notice is that you will need there'll be 4 conditions. Okay, the fourth condition comes because of acceleration, and then you will have 4 for the first part, 4 for the second part, so you'll have a third order polynomial. Let me just write this down because it may not be very obvious to some of you. Okay. One sec. Okay, so let's write the 8 conditions. So first of all, q10 is 0. Okay, that's these two now. This is what I'm writing. Q1 at t equals 1 equals 0.5. Next, we have the velocity at the start is 0. Velocity at the end of the first half is sorry, that's not given, right? Okay, so those are the three conditions we get. Then we can have the conditions on Q2. At Q2 at time t equals 1 is the same as what you would get at Q1 at 1.5. Then we have Q2 at time t equals 3 equals, see, it's 0.5 to 1, so 1 radian. And then we have Q2 at the end equals 0. Okay, so that is the third one. Okay, now what about the rest? We only have 6. What about the other 2? Well, so we note that the acceleration of the joints at the intermediate point at t equal to 1 should be continuous. What this means is that if you take the acceleration at time t equals 1 for the first half, so imagine q versus t, this is q, this is the first part, or q1, this is q2. So the position is continuous is given by this condition. This one in conjunction with this one ensures that at the intersection, this is 0.5, it's the same value. However, we also need to ensure that q double dot at t is continuous. So this is q2 double dot, q1 double dot. Okay, so this piece here at time t equals 1 should be continuous, which can be imposed by setting q1 double dot at 1 should be equal to q2 double dot at 1. Okay, now even though I just stated the acceleration should be continuous through this statement here, we also need to ensure the velocity is continuous, because without velocity being continuous, we cannot ensure acceleration is continuous. So what we also need to do, and this is not stated in the problem, but something which falls from having the acceleration being continuous, is that q1 dot, q2 dot, this point here at time t equals 1 should be continuous. So that condition is q1 dot at 1 equals q2 dot at 1. Okay, so what we have here is 3 conditions here, 3 here, 1 here, 1 here. So total is 8 conditions. So we have to have uh, third order polynomial for q1 and q2. Okay, so begin of assuming q1 of t equals a10 plus a11t plus a12t square plus a13t cube, and q22 equals a20 plus a21t plus a22t square plus a23t cube. Okay, and then you will have to find the first derivative of q1, first derivative of q2, second derivative of q1, and second derivative of q2. Okay, and then I think there's no point in me actually spending the time and doing this step by step like I did for the previous problem, because essentially the same sort of recipe. You basically do this derivatives, you put in the 8 conditions, you end up getting an equation which looks like ax equals b. I'll write that equation down so that way you can compare what you get when you do it yourself with my answer. So what I get is the following equation. So fill in the equations yourself and see, and you can check if you get this. Zero, zero. Okay, that's the first line. 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. Sometimes it's easier to visualize it if you draw a vertical line like this, or if you have a grid-based paper, it's just much easier to visualize it if you write it in those boxes. Okay, so here is the A matrix, and then we have the unknowns. Missing something, A20. That's what I'm missing, A21, A22, A23. And then the right hand side is simply 0, 0 0.5, 0 0.51, 0, 0, 0. So a x equals b and x equals a backslash b. Now, when I wrote down these equations, one thing to remember is when you do it yourself, you might see that your A matrix looks a little different from my A matrix depending on how you arrange the equations. Okay, so if you, for example, switch equations 1 and equations 2, right, you'll see that these rows will get replaced, they will be swapped. Okay, that doesn't mean that your equation is wrong or my equation is wrong. It just means that your equations got swapped, which means that some of your rows have got exchanged, and that really doesn't really affect the final answer. So what you want to do is, instead of checking the A matrix with this, you want to check what values you get for the coefficients. These are the values I get when I crunch this in MATLAB. So if you use these values to make plots of Q versus T, then you see something like this. Okay, this is about 1. And if you look at Q dot, it actually looks something like this, where 1 is somewhere here. And then Q double dot shows this pattern. This is actually 1, not that, not this piece. So what you notice is that compared to the previous plot, here are a few things you note which are different. One is that you see that here the velocity is not 0. If the velocity was 0, the slope would have been 0, right? Something like this. It's not true. In fact, if you look at the velocity is at a peak. It's not 0. Then what you notice is that at time t equals 1, the acceleration here is continuous, right? It's continuous because these two lines on the right hand and left hand side of this vertical line I drew are touching at one point. So it's continuous. Okay. You, however, do have this thing where the acceleration is not continuous here. Okay. It just happens that the acceleration is 0 here, but here it is discontinuous, which is, as I said, not good for motors. So you get totally different responses depending on what conditions you set at the mid position. Okay, here you see that these plots are much different from the plots I got earlier. So what I'm going to do is I'm going to give you a file in MATLAB called example2.m, which finds these coefficients and then does this plot, so you don't have to do it manually. Okay, any questions on this?